Hey guys, today we will be going into a continuation of the hypothesis tests. You'll remember that before we ran a hypothesis test for a 1 proportion. We're still working with proportions, but this time we have 2 samples, so 2 different proportions, and we're going to use a hypothesis test to see how they compare to each other. So this is the kind of scenario that you'll be seeing where you need to compare proportions. So let's say we surveyed a bunch of teenagers and we found that 57% of the 248 boys that we surveyed had social media, while 70% of the 256 girls we surveyed had social media. So what can we do with these numbers? We could make a confidence interval about the difference in the proportions. So we could make a confidence interval about the true difference between the percentage of girls with social media and the percentage of boys with social media. And then we could also run a hypothesis test to see if there's really a significant difference between genders in the proportion of people with social media accounts. So the first thing on the list was making a confidence interval about the difference in proportions. So this is to make an estimation about the difference between the two groups. Earlier we had 70% of the girls with social media accounts and 57% of the boys with social media accounts. We're not making any estimations about this 0.7 or this 0.57. What we're making estimates about is the true difference between these two. So what percent more of girls have social media than boys? So the number that we'll be doing math on would be the 0.7 minus the 0.57, because we are interested in the difference in proportions, not the individual girl social media numbers and boy social media numbers. So what are our important numbers? Before we only had a p-hat, an n, and then we just did all of our math based off of those. Now we have a p-hat 1, a p-hat 2, so these are our 0.7 and our 0.57. We have an n1 and an n2, so this is the sample size of our first sample, and this is the sample size of our second sample. So if we decided to put girls as our first sample, then our p-hat 1 would be 0.7. Our n1 would be how many girls we chose to sample, so that would be 256 girls. And then our n2 would be the number of boys we chose to sample, so that would be 248 boys. And then we have a p-hat difference, so that is equal to p-hat 1 minus p-hat 2. Or p-hat 2 minus p-hat 1, it really doesn't matter as long as your answer comes out positive. There's always going to be some conditions that you need to satisfy in order to be able to create a confidence interval. So these are your 4 conditions. Again, these are basically the same as before. We have independence condition, randomization condition, 10% condition, and our success failure condition. The only one that really changes is our independence condition. Now, instead of just checking for independence within our group of girls, so instead of just checking that whether one girl has social media affects whether another girl has social media, we also have to check to see if there's independence between the two groups. Not only does one girl having social media have to be independent of another girl having social media, we also have to check that one girl having social media does not affect another boy having social media. We have our 2 groups, girls, and we have our boys. We check for independence within the girls, and then within the boys, and then between the 2 groups. So does the girl group affect the boy group? Next, we check that we have a random sample. We sampled under 10% of the entire population, so we sampled under 10% of all girls and under 10% of all boys. And then we have to check our success failure. So this is where things get a little bit weird because we have so much more numbers. The things that you check really varies from class to class, so I'll show you both ways and how they both work. The first way is a little bit longer. You need to show that your n1 p-hat 1 is greater than or equal to 10, your n1 q-hat 1 is greater than or equal to 10, and then do the same for your other sample. So n2 p-hat 2 is greater than or equal to 10, and then n2 q-hat 2 is greater than or equal to 10. So this is what you will normally write when you're doing confidence intervals. You won't need any other numbers, this is all you need. But when you run a hypothesis test, things will get a little bit different, and I'll get to that in a minute. This is the math for your confidence intervals. The actual formula is down here. The stuff above looks a little bit crazy, but it's not as bad as it looks, trust me. So again, you have your confidence interval centering around your p-hat difference. So you're making an estimation about the true difference between the two groups. Your z-critical value has not changed, and then you still need a standard error to multiply with the z-critical. So the one thing that really changes here is the way you calculate your standard error. Now you have two different standard errors, one from each sample, and what you need to do when you calculate your confidence interval is to combine these two standard errors. What we need to find first is the variance of the difference between the two proportions. So that would be equal to, since variance is equal to standard error squared, our standard error is equal to the square root of the variance of p hat 1 minus p hat 2. Even though we're subtracting p hat 1 from p hat 2, going back to random variables, you might recall that variance is always added to itself. Variance is never subtracted, only added. So from here, we can expand it outwards into the standard error of the difference in the two proportions is equal to the square root of the variance of p hat 1 plus the variance of p hat 2. So what are these two variances equal to? So the variance of p hat 1 is equal to the standard error of p hat 1 squared. And we know the standard error of p hat 1, there's a formula for it, and that would be the square root of p hat 1 times q hat 1 over n1. It's just our square root of pq over n again. I included the sub 1 because we're talking about two different samples and I want to clarify which sample we're using. And then you just leave the big squared on the outside. But then since we have a square root here and then a squared, these two cancel out. So we have a final answer for the variance of p hat 1, which is p hat 1 q hat 1 over n1. So we can plug that in over here in the place of the variance of p hat 1. And doing the same thing for sample 2, just changing the subscripts, we can put in the variance for p hat 2. So this is the standard error formula for a confidence interval between two proportions. Putting that into practice, we have the same scenario from earlier. After surveying a bunch of teenagers, we find that 57% of the 248 boys had social media, while 70% of the 256 girls had social media. Construct a 95% confidence interval. So first, we have to list out what all of our important numbers are. So first we need our p hat 1 and our p hat 2. It doesn't matter whether you assign the girls or the boys to be p hat 1 or p hat 2, but my personal preference is to put the bigger proportion as p hat 1. So I'm going to put the girls as the first sample, so 0.7, and then the boys as sample 2, so p hat 2 is 57%. Now that we have our p hat 1 and p hat 2, we can directly get our p hat difference. So this is equal to, again, the absolute value of 0.7 minus 0.57, which is equal to 0.13. Next, we need more numbers to calculate our standard error. So we need our n1. That is the sample size of our girls sample, because we assigned girls to be sample 1. So that would be 256 girls in sample 1, and then 248 boys in sample 2. We have basically all the numbers that we need to make our standard error now. So the formula for standard error was the square root of p hat 1 q hat 1 over n plus p hat 2 q hat 2 over n2. Plugging everything in, that would be our p hat 1 of 0.7, q hat 1 of 0.3, because 1 minus 0.7 is 0.3. Our n1 is 256 plus 0.57 times 0.43 over 248. Putting all of that into the calculator, we get 0.0425. So that is our standard error. The last thing that we need is our z-critical value. So we are constructing a 95% confidence interval. This means that we could do one of two things. We could use our calculator function inverse norm to get our z-critical value, or we could take this straight from memory. So for those of you that do not have this memorized yet, we will use our calculator function. So inverse norm, and then we put in an area, our mu of 0, and our sigma of 1. because we are creating a 95% confidence interval, our normal model would look like this. It's not a good drawing, but just go with it. So we have 95% here, and we want this value. So that means our area is everything from negative infinity up to here. And because this is symmetric, that means there's 2.5% on this side. So the area we get is 0.975. And the number we get back out of the calculator is 1.96. So we have all the numbers we need now. We just have to plug it into our formula here. So our confidence interval is equal to 0.13 plus or minus our z-critical value of 1.96 times our standard error of 0.0425. That makes our final interval equal to 0.0466 to 0.2134. Because this is all in proportions, that means our 0.0466 is equal to 4.66%, and our 0.2134 is equal to 21.34%. So what does this tell us? Since we're making an estimation about the difference between the percentage of boys with social media and the percentage of girls with social media, since we always put the larger sample first, and because the girls here were the larger sample, that means that our 4.66% and our 21.34% tell us what percent more of girls have social media than boys. So you would say, I am 95% confident that the true difference in the percentage of girls with social media and the percentage of boys with social media is between 4.66% and 21.34%. Or you could also put it this way, I am 95% confident that between 4.66% and 21.34% more girls have social media accounts than boys. So next we have our hypothesis test. Again, our first step will always be to list out our null and alternative hypothesis. This time, our null and alternative will basically be the same across all two proportion hypothesis tests. Our null will always be that P1 minus P2 is equal to 0. So that is also equal to P1 is equal to P2. We just switched around where the numbers are. I didn't put a hat because for our null hypothesis, we're making a prediction about the actual population, so we don't need a hat here. And our alternative hypothesis is usually something along the lines of P1 minus P2 is not equal to 0 or greater or less than 0. Next we have our alpha threshold. So this is basically the same as usual unless the question specifies otherwise. It's just that alpha is equal to 0.05. Then we also need to list out our p hat 1 minus p hat 2, and then individually what is p hat 1 and p hat 2. Then we also give our n1, n2, and then we have to give a special number called our p hat c, or p hat combined. And this is an example of pooling, where we combine our p hat 1 and p hat 2 in a sort of weighted manner. We have to do this because our null hypothesis assumed that p hat 1 and p hat 2 were the same, so that means that it would be fine to combine our p hat 1 and p hat 2. So this is the ultimate number that we end up using for our standard error calculation for hypothesis test. And that is equal to n1 times p hat 1 plus n2 times p hat 2 over n1 plus n2. Here are the rest of the steps. Next we would do our conditions. So this is our independence condition, randomization, 10%, and success failure. I did mention earlier that there was another way to write your success failure condition, and that's what you do in hypothesis tests. So here you have to include n1 p hat 1, n2 p hat 2, n1 q hat 1, n1 q hat 2, and then you need to take your p combined. So n1 plus n2 times p hat combined has to be greater than or equal to 10, and then n1 plus n2 times q hat combined has to be greater than or equal to 10. Q hat combined is just 1 minus p hat combined, same as usual for all PQ calculations. Some instructors do not require this part, and all they need is your p hat c and your q hat c is greater than or equal to 10. But if you want to play it safe, just include all 6 of these. Next, you would calculate your standard error and get your z-score. So your standard error has to be calculated with p hat c, as I mentioned earlier. And so this one would be equal to your p hat c times q hat c times, and then in parentheses, 1 over n1 and 1 over n2. This is your new standard error. You use the standard error to get your z-score. So that would be equal to your p hat difference minus the assumption from the null hypothesis over your standard error for p hat c. So your p hat difference you already got when you listed out all of your numbers, and your assumption from the null hypothesis is that p hat 1 minus p hat 2 is equal to 0, right? So that means that this number here is just 0. So your final thing should look like p hat difference over the standard error of p hat c. It's also recommended that you put the extra minus 0, even though it doesn't really do anything extra, just to show that you understand what's going on. You would draw your normal model and flag your z-score, and then you would go into your calculator, do your norm CDF function, and get a p-value back, and use that p-value to draw your conclusions. So here is our practice question for a hypothesis test on two proportions. So after surveying a bunch of teenagers, we find that 57% of the 248 boys had social media, while 70% of the 256 girls had social media. Is there a significant difference between the proportion of girls with social media and proportion of boys with social media? Again, our first step will be to list out all of our important numbers and hypotheses. So before we do anything else, we have to set which sample will be our sample 1 and which sample will be our sample 2. So we write up at the top, let p hat 1 be equal to the proportion of girls with social media, and let p hat 2 be equal to the proportion of boys with social media. Now that we have assigned sample numbers to each group, we can list out our important numbers. So what is our null hypothesis, first of all? Our null hypothesis will always be the same thing, that p1 minus p2 is equal to 0. Not p hat 1 and p hat 2, but p1 and p2. Our alternative hypothesis is that, going back to the question here, it only asks if there's a difference. It doesn't ask if the girls have more social media accounts or if the boys have social media accounts. It's not asking for which one is bigger. So because there's no direction specified, we can just say that p1 minus p2 is not equal to 0 for our alternative hypothesis. And then we give our important numbers. So p hat 1, since we said it was the girls, it's 0.7. P hat 2, because it was the boys, 0.57. N1 is equal to 256. N2 is equal to 248. Our alpha value is 0.05 because it was not specified in the question. And then we need our p hat c. Geez, I'm running out of space. So our p hat c is equal to n1 p hat 1 plus n2 p hat 2 over n1 plus n2. Putting in all of our numbers, we get 256 times 0.7 plus 248 times 0.57 over 256 plus 248. Putting that into a calculator, we get 0.636. So that is our PC, 0.636. Next, we have our conditions. So we start off with independence. We have to check independence between and within groups. So we would say something along the lines of, whether one boy or girl has social media should not affect if another boy or girl has social media regardless of gender. So that takes care of both within and between groups. Next, we have our randomization condition. We don't know that this sample is random, but we also don't have reason to believe that this sample is not representative of the entire population, so we just put our kind of wishy-washy BS statement here. Although the sample was not randomly taken, we have no reason to believe that the sample is not representative of the population. Next, we have our 10% condition. So there are definitely more than 2,480 boys and 2,560 girls in the world. So our samples are definitely less than 10% of the entire populations. Next, we have our success-failure condition. So this is where we have to compare our N1 p hat 1 N2 p hat 2, do the same thing for the Q's, and then the same thing for our p hat pooled. So because all of these comparisons were satisfied, all of these numbers were greater than 10, then the sample is large enough to apply the CLT. And finally, since we satisfied all of our conditions, we can proceed with whatever we're about to do. So that is the name of our hypothesis test. The name of that test was split into 3 parts: the number of samples, whether we're doing proportions or means, and then a z-test or a t-test based on whether we're doing proportion or means. So only one thing has changed here, the number of samples that we're using. So instead of 1 samples, we have 2. We have a sample of boys and a sample of girls. So we have a 2 proportion because we're working with proportions. And then we're running a z-test because z-tests are always used on proportions. So because the conditions are satisfied, we can proceed with a 2 proportion z-test. Now that we've satisfied our conditions, we can go ahead and get our standard error, and with that, get our z-score. So the first thing we need to do is get that standard error for p hat c. So the thing with p hat c is that you only use it in 2 places. Once is in the success failure condition, and then once is for the standard error calculations. Once you get your standard error using p hat c, you can just throw it away. You really don't need it again. So this is equal to the formula that I wrote down earlier, which is p hat c times q hat c times 1 over n1 plus 1 over n2. And this is equal to, substituting everything in, 0.636 times 0.364 times 1 over 256 plus 1 over 248. Putting that all into the calculator, we get 0.0429. Now that we have our standard error, we can get our z-score. So the formula for the z-score is equal to our p hat difference minus our assumption from our null hypothesis. I'm putting in the null hypothesis symbol as a placeholder. This is not really correct notation. And then it's all over our standard error for p hat c. Plugging everything in, our p difference is up here, 0.13, minus our assumption from our null hypothesis. So we assumed in our null hypothesis that p1 minus p2 is equal to 0. So it's 0.13 minus 0 over our standard error of 0.0429. This is all equal to 3.0325. Now that we have our z-score, we can flag this on the normal model. So that is our step 4. Since it's the standard normal model, we label our mean as 0, and then 1, 2, 3. There is our z-score, and we're interested in everything from here to the nearest extreme. So this area right here. Next, we go on to step 5. So that would be putting everything into the calculator. So what we want to know is the probability that any z-score, any data point, ends up at our z-score or greater. So greater than 3.0325. And we can get that through our norm CDF function. We need to put in a lower bound, an upper bound, a mu of 0, and our sigma of 1, because we've already converted everything to the standard normal model. Our lower bound, looking at our normal model, would be 3.03, and then we're moving to the nearest extreme, so infinity. But then there's one more thing that we need to pay attention to, because coming upwards to our alternative hypothesis, there's a not equals here. So not equals means we're not only looking at this side of normal model, we need to look in both directions, because it's saying P1 could be the greater proportion, but P2 could also be the greater one. So not only do we need to look at this area, we also need to look at the area from negative 3.03 to negative infinity. We don't have to draw that on our normal model, but I'm just putting it there for visual reference. So what we need to find is not just this area, but also we need to find this area plus our lower area here. Thankfully, these two are equal, so we can just put a 2 times here. So 2 times of this area is equal to our upper area plus our lower area. And that is equal to 0.00243. And that is our p-value. So this is the probability that such a large difference between the percentage of girls with social media and percentage of boys with social media would occur if there was no difference between the two proportions. So now that we have our p-value, we can put our conclusion. I had to zoom out for this one. I overestimated how much space I had left. If there was truly no difference between the proportion of girls with social media and the proportion of boys with social media, the probability of the observed data occurring would be 0.243%. Because the p-value is so small, make our comparison 0.00243 is less than alpha, which is equal to 0.5, I reject the null hypothesis. We have sufficient evidence to believe that there is a difference between the proportion of girls with social media and proportion of boys with social media. That last sentence isn't really necessary, that's why I didn't write it, but if you want to play it safe, you can definitely add that. So that is it for a two-proportion hypothesis test. From now on, we'll basically be running off of the same template for the hypothesis tests on means and two means. So everything should get a lot more familiar from now on. So thanks for watching. Hope you learned something. Peace.